Hello everyone, I hope you guys had a wonderful Thanksgiving. I know that I did, even in the kind of odd year that we're having. But it is, of course, time to get back into the wonderful world of geometry, and what we are going to be doing today is looking at Circumcenter and Orthocenter, and if those look like terrifying words, don't worry, they aren't that complicated, they're just big words. So let's look at a familiar term before we get into Circumcenter and Orthocenter, and that is perpendicular bisector. Now, you guys know that a perpendicular bisector is simply a line that comes through the midpoint of a segment. So this one comes through the midpoint, right, because it's cutting this segment into two equal pieces, and that's the bisector. But it's also going to be perpendicular, which means it comes through at 90 degrees. So anytime I see it's coming through the midpoint at 90 degrees, I know I have a perpendicular bisector. And it doesn't matter if it stops when it hits the segment or comes all the way through the segment, both of those are perpendicular bisectors. But today what we're going to learn is one other smaller fact about it that turns out to be quite important. And that is that any point on the perpendicular bisector is equal distance from the endpoints of the segment it bisects. So that means if I just pick a random point, and it really doesn't matter where I put it versus where you put it, I will be able to make two equal segments simply by connecting that point to the end point. So these two should be equal lengths. And by the way, even if this was not marked as the perpendicular bisector, if it turned out that this and this were even, it would mean that this line would have to be the perpendicular bisector. Now, like I said, it doesn't matter where you put the point. It can come underneath the segment down here. It can come above the segment way up here. Regardless, you know that the segments formed will be congruent. Now, be careful, they are not congruent to each other. So this one is obviously not congruent to this one down here. These are very different lengths, but it will be congruent to the other segment connecting an endpoint to that point on the perpendicular bisector. Now, we're going to be using some of those ideas as we go, so just kind of keep that on the back burner, maybe add it to your notes right here. By having all of these down, of course, we have another tool to use later on to find more information on problems that we're stuck on. But we're also going to use this idea to talk about circumcenter and circumscribed circles. So let's look at that. So when we're looking at circumcenter and circumscribed circles, what we're going to be having to do is find the perpendicular bisectors of each of the sides of the triangle. And in order to do that, you're going to need a compass. Now, you can use the same sort of compass that I'm using, or you can use kind of the traditional compass that's something like this, or any other variety. Dollar stores have them, Myers has them. Just go ahead and get one that you feel comfortable with. Just remember that the center on these ones is this. This is going to be the center of the circle. And my radius will be formed by whatever circle I pick on here to spin it around. So I'm going to start by finding the perpendicular bisector of this triangle on the right. And in order to find perpendicular bisectors on this triangle, what I'm going to have to do is I'm going to have to select a side that I want the perpendicular bisector of. So I want the perpendicular bisector of this side. So I'm just going to kind of like highlight it, and that way I can find it easily. Now the next thing that I'm going to do is I'm going to find a perpendicular bisector of that by putting my compass on the vertex of one of the sides, so the end point of one of the sides, and I'm going to actually select the end point or my radius to be the same as the other endpoint. So my center's on the center. I've picked the hole that lines up best with that other side. And it is really important that you are careful here that you don't bump things or move things over, because as soon as you do, all of your answers will be a little off. And let me zoom out just a little bit so we can see this, because this is going to need a little bit of space here. So once I have this half circle, I don't need to go all the way around. I just need about half of it covered, and you want the half in the direction towards that other vertice. I can go ahead and reverse the process. So what I'm going to do is I am going to put my center on the other vertice, and I'm going to select the other end point so that I can form another semicircle here around the other side. Notice you should be using the same hole on your compass, or the same length for your compass. So this is what I ended up with, which is like kind of a weird fish shape. And what I'm going to do is I'm going to connect the two overlapping points, so those 2 points of intersection, I'm going to connect those. And what I've just done when I do that is I've found the perpendicular bisector of that line segment. Now, because of the nature of the triangle, it's going to make one side look a lot shorter than the other side because this side's so much smaller than this. But these should be pretty close in length. They might be a little bit off due to compass error and user error, but it should be really close. Now, once I have this, I like to go back and erase my work lines so that I have less lines to focus on the triangle itself. That's why it's nice to do the work in pencil and do your answer in pen so that you can kind of clean up your problem. So I'm going to repeat this process with each of the other segments on the triangle and show you what it should look like in the end. Now, as you can see, I left all my work still on these two sides, so I could go ahead and erase that work so that you're left with just the key pieces, or just those perpendicular bisectors of each of the sides. And that will allow us to have a little bit less to look at when we're looking at this triangle mess that we've made. Now, when I look at this, I can see that I found each of the perpendicular bisectors of the side, and notice something strange. They all fit or intersect at the same point. Now, if yours do not, it means that you didn't do a neat enough job when you were finding those. So your circles got bumped, or your radiuses got mixed up, so it might be slightly off, like you might end up with one line coming through just slightly off from the other two. And that would be the line that you'd want to, or like you'd want to look at that line and kind of adjust each of them until they come together at the same point. Now, this point right here that we found, the intersection of the perpendicular bisectors, is what we call the circumcenter. And the reason why we call it the circumcenter is because we can actually form a circle that goes through each of the vertices of this triangle simply by putting our compass on that center and picking one of the vertices. So I'm going to go ahead and use this point here, and I'm going to go through each of those. Now, mine's slightly off, right? It misses this one by just a little bit and this one by just a little bit, but that is pretty close to exact. So if I went all the way around here, continuing this on, I would have a full circle that goes through each point on that triangle. Now, what we've just done is a circumscribed circle. And it's circumscribed because it is going through the vertices of a shape that we give it, like a polygon that we have provided. So the circumcenter helps you find the circumscribed circle, because once you have the circumcenter, or the intersection of the perpendicular bisectors, you will be able to find the circle that intersects each point on the triangle. Now, sometimes, of course, we aren't dealing with perpendicular bisectors and circumcenters. Instead, what we are dealing with is altitudes and what we call orthocenters. Altitudes are going to be something that you use a lot. And altitudes come at 90-degree angles to the base, and you're basically thinking you're trying to find the height of the triangle. And when I'm looking at a triangle in its base, the altitude is just going to drop down straight down to that base at a 90-degree angle. Now, it does not need to be inside the triangle. So if I'm looking at this side here, and I wanted its altitude, or its 90-degree angle there, what I'm going to be looking for is what line could I draw through and get a 90-degree angle? Well, I can't do that anywhere inside of here. In fact, the only place where I'm going to get a 90-degree angle is outside of that triangle. So this would have to be the altitude of that triangle according to this base. So this right here is my altitude. Now we can, of course, extend that line down if we decided to. It doesn't need to stop there, though the altitude itself is really only the length from here to that baseline. And in these triangles, they can take place inside the triangle or they can take place outside. So for instance, this one would be inside the triangle. If I'm dropping that 90-degree angle down to this base, I'm going to end up with one that comes through at about here. And it's pretty close to being the bisector, but it's not quite. So remember, with altitude, you are going to have something that's 90 degrees. It just won't necessarily bisect. In fact, the only time it will also be a bisector is if you have an isosceles or equilateral triangle. So down here where I have an isosceles triangle, if I drop down that perpendicular bisector, it will split this triangle base into two equal pieces. So as soon as I see this marking, by the way, I know that since this is the perpendicular bisector, not just the altitude, that means that these two sides of the triangle must be equal, and this would have to be an isosceles triangle with the equal base angles. And when you're dealing with an equilateral, all of the altitudes will end up being perpendicular bisectors to that base. So all of them will end up here. And you'll see that your orthocenter, or I'm sorry, we'll talk about that. It is the orthocenter. But you'll see that its circumcenter, the point where the perpendicular bisectors intersect, is dead center in the center of a triangle when it is equilateral. And that only takes place when it's equilateral. Even the isosceles will have one that's slightly off because of the perpendicular bisectors of the other two sides. So in this case, that's going to be a special situation. So whenever you see that like special situation, you go, oh, that's an equilateral. Now, most of the time, our altitudes are going to intersect in like kind of weird places. So if I wanted to find the altitude, all of the altitudes of this triangle, I'd be paying attention to each base one at a time. So I'm going to spin this real quick, and I'm going to look at the altitudes of the other bases. So like this base right here, see how this is an obtuse angle? It means that I'm not going to be able to drop a 90-degree angle inside the triangle. So I'm going to extend the base towards that vertice that's kind of overhanging it to find that altitude. And again, I'm going to kind of carefully place my protractor. We are eyeballing these altitudes. They will not be exact because we're not finding the exact right now. And I could drop it on down, and this right here would have to be my altitude. Again, 90 degrees, but definitely not splitting my base in two. And I could find it for my final side, which will actually have an altitude inside the triangle. And here, again, I'm lining up my vertice. I'm trying to find where it comes through 90 degrees to its base. And when I do so, I can extend that line up. The actual altitude is right here. But the extended altitude, the extended perpendicular line, does point up. And notice how they all come together here. All three of my altitudes, if I extend them outward, come together at this single point. And that point could take place inside the triangle, like where we have that equilateral, and even the isosceles, that will take place inside the triangle, or it could be outside. It doesn't much matter. What does matter is that they all come together to that single point, which is called the orthocenter. And the orthocenter is just where the altitudes intersect. The orthocenter does have some important qualities, but right now I just want you guys to be concerned with how to find them. And just be aware, the only time where an orthocenter will be the same as the circumcenter, the intersection of those perpendicular bisectors, will be in an equilateral triangle. So in an equilateral, the orthocenter equals the circumcenter. And guys, that is everything for today. Check out Classroom for the small assignment that you guys have, and I hope you have a wonderful day.